So we've looked at single phase generation, where we've got a single rotor and a single stator and one resistive load connected to that, coil slots A1, and we end up with a resultant waveform of EA1. And again, we're going to look at this from the perspective of a resistive load. And so if we've got that supply voltage EA1 connected across that resistive load, you'll recall that your current is going to be perfectly in phase with that load. And so you can see that your peaks and your zero crossings all align themselves on this graph from 0 through to 360 degrees. As we rotate the rotor through one full revolution, we'll get one full electrical cycle out. Now also recall that the power that's generated by this generator and delivered to that resistive load, although it's going to have an average, because this is a sine squared wave, it will of course have an average where PAV is PM over 2. Max power right there, PM, whatever it might be. If it's 100 watts, the average power delivered to that load is 50 watts. So as far as the load is concerned, as far as joules per second on average, you're going to have 50 joules of energy every second on average delivered to that load. So if it's a light bulb, it's going to burn approximately as brightly as if it was connected to a DC supply that was providing 50 watts continuously. But remember that since the power is actually being delivered in pulses, that the load applied to the prime mover is going to also be required to be delivered in pulses. And that's going to yield a machine that is both noisy and vibrates. And so a very simple and elegant solution to that problem is to introduce what's called polyphase generation. And so I'm going to just simply take this single phase stator out. I'll leave everything else intact, and I'm going to replace that with the polyphase stator. And you can see the only difference between these two is that instead of having one single set of coil slots for coil A1, I've now cut a coil slot B2 into this stator as well. And so what I can do then is to coil B2, I can connect a separate but identical resistive load. And in reality, it actually doesn't even need to be identical. But for the purpose of phase balancing and trying to smooth out the load to the prime mover, we need to make them balanced. So I'm going to connect load R2 up to the other coil, up to B2. And so I'm going to just simply say that R1 equals R2. Now, if that's the case, what have I done mechanically to change the generator? Well, as far as weight is concerned, I've made a negligible impact whatsoever on the actual stator, because what I've done here is I've carved out iron laminations, and I've replaced them with copper wire. So essentially the overall density of the motor remains unchanged. The total weight of the, I'm sorry, not the motor, the generator. The total weight of the generator remains unchanged, and yet I've added a complete second separate generating coil, which means I can provide power to a separate load. So you can almost think of the polyphase generator as two separate generators acting in unison with each other within the same housing. Now you might think, well, that seems perhaps a little bit silly. Why would I really want to do that? And it comes down to the effect that this has on the actual prime mover and the overall total power output that's delivered to our loads. Okay, so here I've got the same rotor that's rotating on one common shaft, and something different is happening to the two different coil slots as that rotor rotates. Right now, in this position that the rotor is in, you recall that the magnetic flux lines are leaving the North Pole. They're crossing coil slot A. They're traveling through the stator, and they're traveling back into the South Pole of that magnet. So at this position, we're going to call that position 0. We're going to have the highest or the largest peak induced voltage on coil AA1. And that's what's indicated here on this graph. So at the exact same time, coil B2 is going to be at its lowest point. It's going to be at its zero crossing. Why? Because all of the magnetic lines of flux are traveling here, crossing coil A1. None of them are crossing coil B2 right now. And so if I just grab a different color and I apply that different color to plotting a second graph, I'm going to start, and I'm going to call that coil voltage EB2. So right now, at the exact same time that EA1 is at its peak, B2 is at its minimum, or at 0. So as I rotate now through 90 degrees of mechanical rotation, you should now be able to see that coil B2 should be at its peak, while coil EA1 is at its zero crossing. Another 90 degrees of rotation, and that puts EA1 down at its negative peak, but EB2 is going to be at a zero crossing. We go through to 270 degrees, and now B2 has completely reversed polarity, so it's at its negative peak, EA1 is at zero, and then we finish up at our original starting point, 360 degrees of rotation, or back to zero, and we're exactly back to where we started. So if I connect the dots, of course I could do this with a much larger number of data points, but I'm just going to connect these dots. We know that it's going to be sinusoidal in nature, and I'm going to call this EB2. So what we see here is that we now have two waveforms, the red waveform and the brown waveform, and they are both mechanically and electrically separated by a phase shift angle. In this case, the peaks are separated by 90 degrees. As well, the zero crossings are separated by 90 degrees. 90 to 180 is 90. At every 2 points, you could pick any 2 points on these waveforms, and they will always be phase shifted by 90 degrees. And we would say that EB2 lags EA1 by 90 degrees. So that's the waveforms that are generated. Now, what effect is that going to have on the power that's generated by the polyphase generator? So if I'm going to come down here to my power graph, you'll recall, and by the way, we've connected an identical resistive load, which means that, of course, we're going to have a current waveform that follows along EB2 as well, completely in phase with the voltage. That's why I'm just drawing them as dotted lines there. And so since we're 90 degrees mechanically separated, we're also 90 degrees electrically separated. It stands to reason that our power waveform should also be 90 degrees separated. Keep in mind that through 360 degrees of electrical waveform, we end up actually seeing two power waveforms, right? The frequency of the power waveform is twice that of the voltage, and that's because of the effect of negative voltage and negative current. Remember that power is the product of voltage and current, and so we end up with positive power when we have negative voltage peaks because the current is also negative at that time. And so now looking at the second waveform here, we can see that for EB2, when their zero crossings are happening, we're going to have zero power delivered. And when the positive voltage and the positive peaks are occurring, we're going to have our PM. So we're going to have to label these now PM1 for the blue waveform, and then PM2 representing the power delivered to resistor 2. So here, again, following along EB2, when it's at its zero crossing at 180 degrees, we're going to have zero power delivered to the second load. When we have our negative peaks for EB2, our negative current, we're going to get a positive power pulse. And if I draw this waveform here over top of the original power waveform, we can see that we now have two power waveforms that are actually additive and in nature. And because of the fact that these are sine squared waves, the cool thing about them is that they will add completely. If you sum the two waveform PM1 plus PM2, you will end up with a completely perfectly flat line. That's the nature of sine squared waves. And so what we've just done is we've just increased the total average power that's delivered to our loads. Yes, they are separate loads, and I'll come back to that in a moment, but we have just increased the total average power to not PM over 2, but just PM. Meaning that if each of these waveforms independently was developing 100 watts peak, now our total average power delivered to these two loads combined is 100 watts, or 100 joules every second. But because of the fact that when you add PM1 plus PM2, at every point, you add them here, 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 everywhere, they will always sum up to the exact same value. What effect does that have on the prime mover? Well, since the average power delivered to the load is no longer being delivered in pulses, the average power is being delivered as a nice, smooth, continuous, constant, straight, flat line, we end up with the same effect on the prime mover. The prime mover is no longer having to deliver its energy to the generator in pulses. Instead, it's being delivered consistently. Now, you might be wondering, okay, we've got two separate but identical loads. When is this a reality? When would we actually use two separate identical loads in order to smooth out the output of a generator? Well, imagine that you've got, I mean, we're at this particular point in time, we're coming into our fall and then soon winter season. And imagine that your building, whether it's an industrial application or residential, is heated by electric heaters. So I'm going to simply take a box and I'm going to put a resistive heating element in that box. Okay, so if that resistive heating element is representing resistor R1, well, R1 is dissipating an average power of 50 watts. Of course, it's being delivered in pulses. That's the blue waveform here. But if I take resistor number 2 and I also put it into the same box, now I've got 50 watts average being delivered there. That box is representing my electric heater. How much energy is being dissipated into the room around it by the electric heater? 50 joules per second here, 50 joules per second there, or a total of 100 watts or 100 joules of energy every second. It doesn't matter as far as the heater is concerned, and then of course as far as you are concerned standing in that room, you are going to have a smile on your face because you are happy that your room is now being heated at a rate of 100 joules per second. It matters not to you whether resistor number 1 is receiving its power impulses and resistor number 2 is receiving power impulses. You just care about getting 100 watts or 100 joules of energy every second into that room. The same sort of effect can be assumed if you change these resistors instead to light fixtures. Okay, if you want lighting to be happening in a room, if you've got one light bulb that's burning at a rate of 50 watts average and another one that's burning at a rate of 50 watts average, you've got 100 watts of energy. If it's incandescent, we know that 90 some odd percent of that energy is lost due to heat, but you're still getting the same average amount of lighting into that load that each resistor or each load is able to provide, and so you get twice the total by one generator. So the benefit here, of course, is that A, we have reduced the vibration and the pulsating effect on the prime mover. We've reduced the noise as well. If this prime mover is not delivering its power impulses, it's also going to be less noisy. And with the same mass, as far as the generator is concerned, we've now been able to deliver twice the average power as the single-phase generator. So it's a win all the way around. Now this is polyphase. This is more specifically dual phase 1 and 2. We're going to next look at three-phase applications, and the reality is you might be wondering how far can we go with this. Well, we could keep going. We could go to 6-phase, 12-phase, but we're only going to look at 3 because the entire power grid is actually a 3-phase power grid, so that's coming up next.